So instead, so let's look at some examples. We have several examples. So example 1. So all these examples, the first goal is to find basis for the two subspaces we introduced earlier, right? Kernel and the image of a matrix or transformation. So suppose we have this matrix A. So how do we find a basis of the kernel of A? And how do we find a basis of the image of A? So this part, so this example and the ones, 2 or 3 after this group of examples are a little bit technical, okay? That means you need to do some homework on it, right? So there are 2 different ways of doing this. In the book they explain using the example. Find basis of the kernel and the image. Sometimes the problems are separated. They ask you to find a basis for the image of matrix A. And then some of the problems are specific about finding a basis for the kernel, right? But then some other problems, it's possible to ask you to find both, right? To find both a basis for the kernel, a basis for the image. Okay, so in the third case, you have a choice, right? You do the kernel first or you do the image first, right? In the first 2 cases, you don't need to think. They ask you to do this image of A. Okay, so you just try to do that. But what if you have choice? So keep that in mind when we look at this example. So first one, let's look at this example 1. We have a matrix A, which is what? 4 by 5, right? 4 rows, 5 columns. So find the basis of the kernel of A. They put this as A. That means let's do it first, right? Work on the kernel. Find the basis of the kernel first. So how do we do that? We solve the linear system. AX equals 0, right? So A, this is A. We form the augmented matrix. Okay. So here they directly find the RREF of A. Why do they do that? Well, the augmented matrix will have this matrix A, and then you have one more column, right? 0 column. They skip that. 0, 0, 0, 0 all the way, right? 4 of them. 4 rows, 4 zeros. So they skip them. They didn't write that out. You don't need that. When you solve AX equals 0, the right hand side is 0. That's this system is homogeneous, right? So usually augmented matrix, we just write A. We don't need to write 0, 0, 0, 0, right? And then the second, they already found RREF for us, right? So there's some work in it. So for instance, what do we do in the first step? What is our first step? So we should use this leading one, right? This leading one to eliminate -1 and then 4 and 3, right? Then we go on. So but they did that for us. Okay, so what do we see here? First column is 1, 0, 0, 0, right? Second column, 2, 0, 0, 0. And then remember, we we need to find we need to solve this system. And then now, how many leading ones? I already circled, right? 2 leading ones, right? So these 2. So these are the leading ones. Here and the thing. 2 leading ones. And then 3 variables. So 5 minus 2, you get 3. So that's how we count. How many free variables? So these 3 variables are called S, T, and R. So S, T, and R. So you look at this table, this vector whose components are x1, x2, x3, x4, x5. You see 2, 2nd, 4th, and the 5th. They are already known. S for x2, T for x4, R for x5. What are these 3 letters? They are free variables. Any real number. They are independent, right? R can be any real number, T any real number, right? S. So using these 3 S, T, and R for x2 and x2, x4, and x5. We solve for the remaining 2 variables, which are the leading variables, right? So we find them. One is x1 is negative 2s minus 3t plus 4r. So you see this is not a matrix, okay? This is not a matrix. We need to know that. It's continuous. Negative 2s minus 3t plus 4r. Is this a little bit confusing? No, it's good. Because
it's just arduous.
Because we can tell from here, they are this column vector, right? They are the components of this column vector. So that's why there is no confusion literally, but still I want to emphasize that this is one formula, right? One formula. But they separate them. That's what we often do. So the first column has only S in it, and then some 0, right? The second has R, has T, and then some empty place. And then R for the last column. I call them column actually, they are not separate. Column, not yet, but I'm about to separate them. And the sum of 3 column vectors, right? And I separate them and then pull out S from the first column, pull out T from the second column, and then pull out R from the 3rd column. If there's an empty place, I add 0, right? So 0, 0 here, 0, 0, 0. So I find 3 vectors denoted by W1, W1, W2, W3. So the conclusion for this part is that these 3 vectors span the kernel, right? Remember what we are doing? We are trying to find a basis for the kernel, right? So what we just did is we have identified that these 3 vectors without S, T, and R, these 3 vectors span the kernel. So let me write this down. So V1, V2, V3. Sorry, W1, right? We use W1 here, W2, and then W3. So they span the kernel. So the kernel of A is the span of these three vectors. So remember, this kernel of A will be the V, is the V, the subspace we are considering. Kernel, okay. So we already find a span. What do? We want to see if there are redundant ones, right? If there are redundant ones, we delete them, right? Reduce the number of vectors to the minimum. Then the remaining ones form a basis, right? Why? Because in the previous 4 statements, we already know if you have some vectors that they span, right? And no more redundant ones. That means the remaining ones are linearly independent. Span and linearly independent. Therefore, they form a basis. Okay, how about this W1, W2, W3? Are they linearly independent or not? Yes. Okay. Why? You look at these 3. So they put it down here. They have the pattern. Remember, we identified. You see, the first one has a 0 here. And then the second one, in the third of the same component, you have a 4 there, right? That means what? The second vector is not redundant, right? It is not a multiple of the first one. How about the last one? You see the 1 here on the bottom. So this one preceded by 2 zeros, right? So this one, the last column vector, is not a linear combination of the first 2. So they are linearly independent. I didn't even put a question mark there. So they form a basis. Okay? So conclusion. These 3 vectors form a basis. Okay, how about top and the dimension? You answer. You count how many vectors are in these bases. 3, right? 1, 2, 3. So the dimension is 3. How about the image of A? The image of A is spanned by these columns, right? So we can write down image of A. So this time the vector space subspace is image of A. It is spanned by the columns of A. So what are the columns? 1 minus 1, 4, 3. And then 2, negative 2, 8, 6. So things like this. 5 of them, right? 5 columns. Okay, so here comes to the point, the main point of this example and the first method. The image of A is spanned by the columns of A. But then it's not so easy to find the redundant ones. You see, the idea is still the same. We already find a spanning set, right? And then we want to find the redundant ones, then we can delete them. The remaining linearly independent vectors that still span image of A form a basis. So we want to identify which one is redundant. So this is not so easy to find. Well, the second one is easy. You see, this one is 2 times the first one, right? So therefore we can say this is redundant. Okay? But then you come to the third. So what do we say? 2 minus 1, 5 point is not redundant, right? Because now we can delete the second one that's redundant. So this one is not a multiple of the first. So we put an N there. But then comes to this two. That's not easy to find without some calculation, right? Without solving linear system. So that's why I put question mark there. In fact, they have a way to handle this. Here is the main point of the method. What they said is, instead of looking at this matrix A, okay, they ask the question, can we look at RREF of A instead? So let's put this back in here, RREF of A. So first of all, why? We want to look at RREF of A because it's simpler, right? Why it is simpler? 1 0 0 0, 2 0 0 0, 2 times the first one is the second. So although we find that easily also from this, but still more to check, right? You need to check 4. Here you need to check this one. 2 0 0 0. Due to those 3 zeros, you only need to figure out that 2 and 1, right? Multiple. And how about those? How about this one? The third, I said not redundant, right? That's also easy to see. 1 and then you have a 0 there, right? How about the fourth and the fifth?
They're both redundant.
They are both redundant and easier to do. We can do that by inspection, right? We don't need to solve. If you do it to the original matrix A, then you need to set up a linear system, right? See if those columns, number 4 column, number 5, right, are linear combination of the preceding ones. Here, we don't need to because we can identify this one, 3 and -4 as what? Linear combination of V1 and V3, right? I should not call them V1, V3, but you understand this is just the first column and then the third column, right? They are not the original V1 and V2 and all this, right? So, but you can tell 3 times the first column minus 4 times the third column give you the fourth, right? How about this one? -4 and 5. So -4 times first column. So here I use B1, B2. This is matrix B, which is RREF of A. So now you see the fourth and the fifth are linear combination of the first and the third column, right? So the idea then is, can we take advantage of it? Can we use RREF of A? It turns out at least the first 2 are encouraging, right? You see, I identified that the second column of A is 2 times the first column of A, right? That corresponds to, in RREF of A, second column is 2 times the first. Not just the fact that the second column of RREF of A is also redundant, but also the multiple is the same, right? 2 times the first one. So let's make a jump, we say. The relation you found over there, in the simple case, RREF, right, reflects what happened here, okay? So let me make it a little bit more precise. So according to the book, you identify a relation. How about that? How do we find the relation? So you look at this RREF of A. What do we find? B2 is 2B1, right? So remember I called the first column B1, second is B2. So B2 is 2B1. That's easy to spot. We found this, and then as all the mathematicians like to do, we put them all in one side, right? So 2B1. 2B1. So put it in what side?
Left side.
Left hand side. So how about we just do 2B1 minus B2 and equals 0, right? How about I add some more? 0B3, how about that? 0B4, 0B5 should be equal to 0. That's the same as saying 2B1 equals B2, right? I add all this 0. Why do I do that? Now I have a relation, right? So remember, this is, the left hand side is this matrix B1, B2, B3, B4, B5 times the coefficients 2, -1, and then 3 zeros equals 0. This is the 0 vector. So we have seen this many times, right? You have a linear combination. You can rewrite this as a matrix times this column vector.
B2 is going to be negative in the.
Well, 2B1, this is equivalent to 2B1 minus B2 equals 0, right? So 2 minus 1, and then 3 zeros.
Okay.
Yes?
I was taking in that one.
Okay. So I'm just rewriting this, putting everything on the same side. And then I find the coefficients of B1, B2, B3, B4, B5. That is the column vector. So what do I do? What have I found? I found this matrix B, right? B times 2 minus 1, 0, 0 is 0. That means this is a solution to B x equals 0. But remember they have the same, so B is RREF of A, right? How do we get RREF of A? Through the 3 elementary row operations, right? We apply one of those 3, and then we just keep finding the good ones. So that at the end I have RREF of A. So each one of those 3 generates a simpler, or, well, the goal is to make it simpler, right? But the main thing is it generates a linear system which is different, right? But equivalent. Equivalent, what does that mean? A and the subsequent matrices or systems have the same solutions. So this one is a solution. Can I say A of this, A times this equals 0 too? Yeah, because this B is the RREF of A, right? So at the end you get something. That's how we solve for AX equals 0. We don't do it directly. We do Gauss-Jordan elimination, right? So at the end you find yourself a solution for the last one, but that's the same. That's a solution to the original AX equals 0, right? So now, how about I write this A out? A1, A2, the columns, A3, A4, A5. I write the columns out. And then I do the same thing, 2 minus 1, 0, 0, 0, copy them down. So this time, I'm going to use the linear combination way to write down this multiplication. This matrix times this column. How do you do it? Linear combination, right? Do we use 2 times A1, right? And minus what? Minus 1 times A2, and then the 3 zeros. 0, A3, 0, A4, and then 0, A5 equals 0. But this one is the same as the one we had before for the b's. You see? So therefore, we again have A2 equals 2A1. So compared to B2 equals 2B1. So you see this? B2 equals 2B1. In RREF of A, you remember that is called matrix B. You saw this B2 equals 2B1. Then you write down the same thing. A2, just replace B1. Change your B to A. You get yourself a relation. I mean, after you put everything in the same side, right? You get yourself a relation. So that suggests that we should use this strategy. We make it very big strategy, right? When what happened? To find, they asked us to find the basis for the image of A. But the image, but A itself is not simple enough, right? For doing it, finding the redundant ones by inspection. Then one way of doing this is to solve Ax equals 0. Or more directly, all I want is RREF of A, right? I find RREF of A. That one is always easier than this one to find the redundant columns, right? So I find the redundant columns, I only put down one. How about B4, B5? They are linear combination of the B1 and B3, right? So from those, you can do the same thing as this B1, B2. Then you will be able to find another solution, right? So another solution, and then that will be, that give you, so you do the same argument, that this will be different. It's not going to be 2 minus 1, 0. That. Anytime you have a relation on the b's, then you just replace the little b by a little a, right? So little a is the A1, A2, A3, A4, A5 are the columns of the original matrix A. So that helps, right? Now, how about the other way? The other way, I mean this. What if my matrix of A already is simple enough for us to find the redundant columns? So this is when the redundant columns are not so easy to find, right? You go to RREF of A. What if you can see it right away? So you find the relation on A, right? Columns of A. Then you can go to RREF of A. That will help you to find vectors in the kernel of A. So that's another type of problems, depending on whether or not it is simple enough or easy enough to find redundant columns of A. So there are two different situations. So let's go on. So in this book, they say, I mean, in this example, they say use RREF of A to find the redundant columns of RREF of A. Then every redundant one you find corresponds to a column in the original matrix, right? Okay. So then you can get it. So at the end, there are two vectors which span. So remember what these two are? They correspond to the B what? B1 and B3, right? So is this A1? That should be A3, right? So you find B1, B3 being the non-redundant ones in RREFA. Then you just go back and then look at the columns of the matrix A. So B1, B3, you change to what? A1, A3. First and the third column. So 2 minus 1, 5, 1. Indeed, that's the third one in 8, right? Okay. So they summarize this method as using RREF to construct the basis of the image. So even you are asked to find image of a basis for an image of A, but you solve the problem as if you are doing AX equals 0. Why? Because you are doing the RREF of A, right? That's Gauss, Jordan, elimination. Okay, so you just go to RREF of A, find RREF of A. Then you can find the redundant ones, delete them, the remaining ones, say B1 and B3. You turn around and go back to A, right? And then use B1 and B3 instead of B1 and B3. Now you use A1 and A3, right? So you find yourself a basis. So to construct a basis of image of A, okay, pick the column vectors of A that correspond to the columns of RREF of A containing the leading ones. That means they are non-redundant, right? So dimension of the image. Dimension of image. So you count how many are left. For this particular problem, we have A1, the first column, and then the third column left, right? So those two vectors form a basis of image of A. But the number 2 is equal to the number of leading ones, right? So therefore, well, number of leading ones is called the rank. So that's why they have this box. Dimension of image of A is the rank of A. And now they come to this very important, so everything is important. So important, but we don't have time, right? So let's do it next time for this. How about the name? Rank knowledge theorem. So we don't even know what this is, but at least I know the name, right?